Okay, welcome class. So on this session, I'm going to talk about stability, and it's going to be stability, and it relates to chapter 15, okay, of the textbook. All right. But before I start that, I just want to last thing we did last class was a little bit on frequency response, and I just want to finish that off and just quickly review it. So frequency response, and then we'll go on to stability. Okay. So the idea of a frequency response, of course, is we have some system with a transfer function of h of s. We apply an input q of s, and we get out an output of x of s. And the idea of a frequency response is that we inject a sine wave into the input, and out comes a modified sine wave, same frequency. That's the key thing. Same frequency, but altered amplitude and phase. Okay, so that's the phase, and that's the amplitude. Okay. All right. Now, the way you can compute this relationship, there are different ways you can do it. You could actually do it in the time domain if you wanted to, but that's really hard. Just by using the convolution integral and applying a sine wave as the input, and then trying to do the integration. That's not going to be easy. You'll still need the impulse response in the time domain. The other way is to do a Laplace transform and actually, get the transform for sine of omega t, which we know, multiplied into hs, and then take the anti-Laplace transform. That's also a bit tedious as well. There's a much better way to do it, and that is to take the Laplace transform back to the Fourier transform, which means setting s equal to j omega, where j is the complex number I. Okay. And so that's what you can do. So to give you an example, and you do this to the transfer function itself. So for example, if I had a first order transfer function expressed like this, all right, I can substitute the s for j omega like that. Oops, wrong one. K2. Okay, I can do that. And in order to find the frequency response, I just have to evaluate the amplitude and frequency that this equation represents. Note that this is a complex number here, okay? Complex number. So it will have an amplitude and a phase component. And so we have to somehow turn this into a complex number that we can get that information from. And so we want a complex number of the form a plus b j. Okay, so once we have that form, we can then get the amplitude and the phase. And to get that for this particular one, the best way is to multiply top and bottom by the conjugate of the denominator. So that'll be right. So I haven't changed anything, right? I'm just multiplying top and bottom, but now I can multiply these two together. And the point is that these two multiplied together will eliminate the complex component from the denominator, and you end up with just a numerator, just a complex term appearing in the numerator, which is what we want. So if you do that, I'll get, and this is in the textbook, but let's write it out. You'll get k1 over k2 plus j omega. That becomes the real part. Minus k1 j omega k2 plus j omega, and that's the imaginary part. So this is the real part, and then this piece here is the imaginary part. And so we have it in this form, okay? We have it in this form, which is what I wanted. Now, if you remember, on complex numbers, if you have the imaginary axis and the real axis, I have a complex number like that. The amplitude or the amplitude or the magnitude of the complex number is basically the length of the vector, okay? And if this is A, if that distance is A and this distance is B, I can just use Pythagoras' theorem to get the hypotenuse, basically. The phase is basically the angle, and I can get that by taking the arctan, okay? So we can do all this now with this number. And if we do that, so if I do that, the amplitude becomes K1 over square root K2 squared plus omega squared, okay? So that's the amplitude comes, and the phase becomes minus tan minus 1 omega over K2, right? Interestingly, the K1 is not involved in the phase. Well, actually, no, it's not involved. Yeah, it's not involved in the phase. And the amplitude just acts as, and K1 acts as a scaling value in the amplitude. So this is one way you can compute the frequency response analytically. Of course, today, a lot of the time you do it by software, and you can do it easily in Python. So maybe I'll give you a demo tomorrow. The other way you can do it is if you have an electronic circuit, you can actually inject multiple sine waves into the circuit and then monitor the response of the system, and you can get a frequency response like that too. All right. Okay. Yeah. And the other way, I was just going to say, because these now get plotted. Okay. So the idea is you would plot these now to form, what we call the Bode plots. The x-axis is always the log of the frequency. The y-axis of the amplitude is usually in decibels, so that's a log as well. And then the phase is often in just raw degrees. Okay. And I was going to say that it's possible, you may have done this with crystallines, I don't know, but there's a way, at least in days gone by, some time ago, there are techniques for constructing the Bode plots graphically given the equations. If you're interested, that's in the textbook, but some people still take that approach, but you can use software these days. Anyway, for this system, which was first order, this is a first order system, right? This is a first order system. Okay. We can actually plot the amplitude and the phase, and we get something like, and you've seen these before, of course. Okay. And there's the bandwidth here, which is 3 dB. Oops, dB down from the maximum. And this point here, which is basically H0, turns out to be the sensitivity of the output with respect to the input. Okay, so it's D output, whatever your output was, with respect to whatever your input was. Okay, maybe we'll come back to that again later on. The phase is actually quite relevant, especially when it comes to think about stability. I just want to write that out again. Degrees. What's interesting about the first order system is that it reaches this asymptote down here. That asymptote is always in the minus 90 degrees for a first order system. Right? Always 90 degrees. It goes from zero, it starts with zero here. So there's no phase change when the frequency is really low, but then because the system starts to lag the input, right? You apply an input and it takes a little while for the output to respond, and that's why we have a negative there. But if you administer very high frequencies, the maximum phase shift you get is minus 90 degrees, right? You won't get any more than that. That applies to any first order circuit, whether it be tank of water, protein in a cell, or a capacitor in an electronic circuit. Doesn't matter. Okay. All right. The interesting thing about this phase shift, which will become very relevant later on, is for a second order system. Okay, which we're not going to drive the equations for that, but for a second order system, if you were to plot the phase shift for a second order system, it'll do something similar, but now the maximum phase shift is minus 180 degrees. So it's added on another 90 degrees. In fact, as you increase the order, you basically increase the phase shift by 90 degrees each time, the maximum, okay? So the third order, it'll be minus 270. For a fourth order, it does full cycle and goes to minus 360 degree phase, all right? So now that doesn't mean the waves are on top of each other. That means one wave is fully 360 degrees out, pushed forward in time compared to the input. All right, so this is something will become important actually when we start talking about stability. All right, so now I want to talk about stability proper. So stability. So as I said, this is chapter 15. Okay, chapter 15. All right. Now we've already talked a little bit about stability, and you know that a system, the solution to a linear system, linearized system, is always some sum of weighted components that look something like this. Okay, it's the sum of some weighted components, and those components involve exponentials. And so long as the lambdas are negative, these exponentials will decay to zero. And if they decay to zero, then we say that the system is stable. Okay. The problem arises if any one of these lambdas is positive. If any one of these lambdas is positive, that exponential will explode, meaning the system is unstable. So pretty much all the methods that are employed to determine stability, except maybe for the method using Bode plots, is involved in some way in looking at the values or the signs specifically for these lambda terms. So I'm just going to list here then different ways that people, different approaches that you can use to work out the stability of the system. The one we've already seen is to get the eigenvalues of the Jacobian or the poles of the characteristic equation in the transfer function. Okay, those are basically identical. There's another one we're going to talk about is called the Ruthowitz method. Okay, this is a tabular method which we'll look at. Oops, it's still used. We'll see why. So the Ruthowitz method. You can also do it using, surprisingly, Bode plots. And in fact, when we start looking at stability with Bode plots, we will come to understand why systems become unstable. Right? Actually, why. There's another one called root locus. Well, I'll just mention that, we won't go into it. There are also polar plots, which I won't talk about. And then there's the Nyquist plots, which I also won't talk about. But those, I think the Nyquist plots might end up in the more advanced course next term. So we're going to talk about what we've really done that. I want to talk about the Ruthowitz and Bode plots, and then a brief mention of the root locus. Okay. All right. So let's have a quick example. I just want to emphasize this bit here. Let's have a quick example of the eigenvalues and poles method. All right. So if you had a transfer function, right, for some system that looked like this. Okay, plus 8. So this is a second order system. We know that because the highest power in the denominator is 2. The way we would do this, if we had the Jacobian, we'd work out the eigenvalues of the Jacobian. But if we had the denominator or the characteristic equation from the transfer function, we just set that to 0 and find the roots. Okay, that's effectively the same as doing the eigenvalues of the Jacobian. Anyway, in this case, we'll end up with -4 and -2. Okay. And because these are poles, these are called poles in the transfer function terminology. The roots of this denominator equation are the poles. And as we mentioned before, last time, people like to do these pole zero plots, and the zeros are the roots in the numerator. Okay. In this case, the root is 0. There's only one, but it's 0. But the pole has two roots, -4 and -2, and so we do a plot of the imaginary axis and the real axis, and we'd plot these then on this pole 0 plot. And in this case, we have -2, which is somewhere around there, and -4, somewhere around there. Okay, so it's -4, -2. Now, the key thing about these plots is what you'll hear often, people asking, are your poles in the left-hand plane, right? They'll talk about that. And what they mean is, are your poles in this section? If they're in that section or in that part of the plane, the system is stable. What you don't want to see are your poles in this section, okay? So if they're in this section, your system is unstable. And if they're in this half, the system is stable. So you might want to ask also what happens when you write on the line that's marginally stable or unstable. Oops, can't spell it. Marginally stable, okay. The other thing we've not talked about at all is what happens if the poles are complex. That almost always invariably means there's some kind of periodic phenomena. So if you find let's say you found there was a pole up here somewhere, that means it has an imaginary part and a real part. The fact it's got an imaginary part means that there's probably some periodic behavior going on. Okay, not necessarily oscillations, but maybe a damped oscillation, maybe a little squiggle in the dynamics, something that's sort of periodic. Okay. So actually, this goes then to the question, I can imagine different patterns for the poles, right? You can imagine them all lying on the real axis on the left side. You could imagine them on the real axis on the right-hand side. You could imagine them being complex on the left side. You can imagine them being complex on the right side. You could even imagine them just sitting on the imaginary line. These are all different sort of combinations that the poles can take. And in each case, there are specific patterns that you observe in the dynamics. And what I'm going to do now is I'm going to stop sharing and I'm going to bring up an application here. Yeah, I think, is this it? Yeah, this is it. So this is a little application. There's a bunch of these online, actually, and I even written one myself, but I can't find it at the moment, so I'm using this one. I've used this one before. It's quite a nice one. It's very interactive. It responds very fast. There are others online, not so fast. Anyway, what have we got here? Okay, what have we got here? You see there, that's the A matrix. So this is a two-dimensional system. 2 state variables. And what we're doing on the right-hand side, this plot is what's called a phase plot. And the 2 state variables have been labeled in this application, have been labeled Y and X, okay? So 2 state variables, Y and X. And what they're doing is they're plotting, so you take one of these green lines. This is a simulation, a time course simulation, okay? So there's some initial condition, and then they run a simulation, they record X and Y. And as X and Y changes, they plot it on here. So you imagine time is actually the distance along this line, okay? So in fact, this system starts, actually time 0, it starts right in the middle, actually. And then as time advances, X and Y change, okay? So they follow this green line, it goes all the way down here. So let's look at one pattern of poles. And what we've got here, the eigenvalues, which are basically the poles. And this is the pole 0 diagram, but without the zeros. It's just got the poles. The green dots are the eigenvalues, okay, or the poles. In this case, they're both positive. So what I'm going to do is I can tweak this here, and I can get the eigenvalues to move. And so what I want to do is, what I'm after is, oh, there we go. So what after is this situation, which is what I just mentioned on the tablet. The two eigenvalues are negative and they're sitting on the real line. Okay, sitting on the real line. The first thing you say, of course, is that the system is stable. And so if you look at the phase plot, you see all the lines. So each of these lines represents a different initial condition. Okay. So I got lots of initial conditions, and then for each one, I just let the simulation run to see where it goes. Okay. So here I've just got 1, 2, 3, 4, 5, 6, 7, 8 initial conditions because I've got 8 green lines. So if you follow one of these, let's say we start with initial condition up here, the y value is this, and the x value is that one down here. I can follow it. And you notice it actually moves into the center. And this center here is basically the steady state. All right. In fact, all the lines here are moving into the center. So this tells you immediately the system is stable, right? Apart from the fact that the eigenvalues are negative as well, the lines are all moving into the center. Okay. All right. So this is a stable system. All right. So this, let me just get the terminology up here. Just get it right. So this, when they're both negative, this is just called a stable system. All right, so this is a stable system. Now, I can also get the eigenvalues to be all positive. Let me see if I can do that. Here we go. There we go. They're all both positive now. All right. And by the way, when I change these sliders down here, I'm basically changing the coefficients in the Jacobian. Okay, in the A matrix. So both eigenvalues are positive, so that means it's unstable. You notice that the shape of the curves is basically the same as it was before, but now the arrows, the trajectories are moving out from the steady state. So this thing is unstable, okay? Right, so those lambda 1 and lambda 2 are the powers in those exponentials, and it's causing the system to diverge, okay? All right, that is called an unstable system. Okay, so let's see. Let's try and do one that's in the positive and negative. Not that. Here we go. Oh, there we go. Let me get it a bit better. No, I didn't want that one, did I? Yeah, let's do that one. Yeah. So this is where one of the eigenvalues is positive and one of them is negative. Now this is an unstable system, but there are stable parts to it. So if you look at the plot, you'll see two of the lines are coming directly in. So this is what's called a saddle node. So you have to imagine an actual saddle, okay? I'll talk a bit more about this tomorrow, an actual saddle to explain what this is. But there's a ridge along the saddle which is stable. If you're exactly on that ridge, you will move towards the steady state. Anywhere else, you will move away, okay? In fact, some of them, like this one here, right, doesn't even get close to the steady state. It starts coming in and veers away. Right. So this in general is considered an unstable state unless you're actually precisely on this ridge, which is very unlikely to happen. All right. So that's called a saddle point or saddle node. So those are all on the real line. Okay. What happens if we get some complex? Let me see if we can get some complex ones. Not that one. Okay. Here we go. Here we go. So now we have two complex numbers. Notice they come as a sort of pair. They both have the same real value, but they actually have opposite imaginary parts. In fact, these are called a conjugate pair. In fact, you can see them here. Look, lambda 1 is minus 0.63, lambda 2 minus 0.63. The complex part, the imaginary part is also the same, but they have different signs, right? This comes from the fact that you remember the equation for solving a quadratic equation. It's what is it? Minus b plus or minus square root of b squared minus ac over 2a. Notice the plus minus. That's why you get a conjugate pair, because whenever you have the complex portion, right, or the root portion, there's always a plus and there's always a minus, right? So in fact, whenever there's a complex component, it's always because that the root part exists, and therefore you'll have a plus and a minus component. Okay. All right. So the fact that it's complex, though, immediately shows you, look, it's a spiral. So this is actually a damped oscillation. Both of the rail parts are negative 0.63. It's in the negative quadrant. That means that the dynamics is stable. Okay. And so it's spiraling into the center. But the fact that you've got an imaginary part means that its trajectory into the center is actually a damped oscillation. Okay. Now, of course, I can do the counter version, which is if I can get it. Here we go. There you are. So now, okay, let's move it a bit. I want to move it out a bit. Oh, never mind. Okay, that'll do. Now both rail parts are in the positive quadrant. I still have it in an imaginary part, but because we're in the positive quadrant, all the trajectories are moving out. Okay, so it's unstable, but they're moving out in a spiral fashion as well. So this means this is actually an undamped trajectory. So it starts off a little wiggle, then it gets bigger and bigger and bigger. Okay. In fact, it goes on forever. Actually, the amplitude of this undamped periodic behavior will expand to infinity. Now, in practice, that won't happen because of physical limitations in the rail system. But in this sort of simulation here, it goes on forever, and the amplitude will keep on increasing. Now these two we had were unstable spiral. This is the unstable spiral, and the other one was the stable spiral. There's one last one I want to mention, which is a bit of an odd one. It's one that's really not of any interest to us. I guess it's not an odd one, but if you're coming from living systems, might be a bit of an odd one. Is this? When it sits right on the imaginary line. If I can get it on the imaginary line, there you go. This looks like an oscillation. It is, but it's not one that we are really interested in. This kind of oscillation is what you'd get from, say, a frictionless spring with a weight on the end. It's a harmonic motion. What you've got here are concentric circles. These circles don't touch. I mean, they don't intersect each other. And so if you were to plot this out in time, you'd see a sustained oscillation. But you notice that there are multiple frequencies in here, all right? Because I got a high frequency in the middle, a low frequency on the outside. So this system admits multiple frequencies, and the frequency you get depends on the initial condition. That's not like the kind of oscillators we deal with in biology or electronics. The oscillator you get in biology or electronics is a fixed frequency. And a fixed frequency in the sense it's independent of the initial conditions. It doesn't matter where I start from, given the same set of parameters, I'll always get the same frequency in the oscillator. Okay. So when you start a heart up, for example, you'll always get the same frequency. Right? It's not dependent on where the heart started from. Right. So, and the same goes for sine wave you generate in a signal generator, for example. It doesn't matter, for what point it started off at, it'll always converge to the same frequency oscillation. This is very different. The difference comes from the fact that these things, the thing you're looking at here, do not dissipate energy. Right? They go on and on forever without because I mentioned a frictionless spring and a weight, right? That'll go on forever, okay? Because it's not dissipating any energy. There's no friction. The things we deal with in biology and electronics, they dissipate energy, okay? And they will wind down once the energies run out. And they have a unique frequency for a given set of parameters. Anyway, I'll talk about this again tomorrow. Anyway, this is called a center, all right? Rail parts are zero, but there's two conjugate imaginary parts. Okay. All right. Yeah, we'll do a lot more of this tomorrow. We'll see if we can do some simulations. Okay. And the textbook in chapter 15 has all sorts of pictures showing you what these look like, both in just simple time course and as phase plots. Right. So remember that terminology. This is called a phase plot, very commonly used in dynamics and control theory as a very, succinct way of showing the dynamics in a graphical fashion. All right. Let me go back then to the tablet. So we'll review this stuff tomorrow, okay? So don't worry if you don't get it immediately. So first I need to share my screen, or stop sharing and then reshare tablet. Okay. All right, here we go. Okay. All right. So I've talked about you can get the stability by looking at the eigenvalues of the poles. We've talked about briefly just now about the different patterns of poles and how they give you different behaviors. So we talked about two negative poles, two positive poles, one negative and one positive pole. Then we talked about a conjugate pair. That includes a real and imaginary part. Okay, and there were two there, one corresponding to a negative real part and the other corresponding to a positive real part. So the negative poles gave you a stable node. Okay, the two positive ones gave you an unstable node, right? The one positive and one negative pole gave you a saddle point or saddle node. Okay, the conjugate pairs either gave you a stable spiral, or if they were positive, it gave you an unstable spiral. Then finally, we had what happens when you have just an imaginary part. So the real part is 0. In that case, you'll get a conjugate. So you'll get something like, plus alpha j minus alpha j. Okay, you'll get a conjugate pair there. And in that case, you get something called a center. Okay, all right. So those are the types. All right. Okay, so the question now is, okay, so you can determine the poles, using this method. Now, these days, of course, it's pretty straightforward to compute the roots of polynomials, but, years back, it wasn't so easy, especially back in the 1940s and 1950s when computers weren't around and all you had was slide rules. So people developed other ways to find out what the poles were. I mean, you could factor them, because you could factor this is just a quadratic and you could factor it, of course. But if you had a polynomial to the power of 4, to the power of 5, what are you going to do? Okay. So this is where a technique called the Ruthowitz method. Okay. Very common method. You do a Google search, you'll find it all over the place. There are also some online tools for doing this for you as well. But it's a tabular method, okay? It's a table-based method, okay? And it depends on some rules governing polynomials. So, what you have to do, you take your characteristic equation. Can I spell that right? Take the characteristic, or let's call it a polynomial. Okay, so it'll be something like, f of s equals 0. That's the denominator of the transfer function. Okay, remember that. It'll be of this general form. You'll have a coefficient s to the n dot going all the way down to a to the n equals 0. It'll look something like that. Okay, and we'd like to know, in terms of stability, whether there are any negative, or really whether there are any positive roots. Are there any positive roots? That's the question we want to ask. Now, the Ruthowitz method doesn't actually give you the values of the roots, but it'll tell you how many positive ones there are. That's basically what it does. Okay. So for a couple of rules first you have to follow, or you have to check. So first of all, number one, if any coefficient, and by coefficient I mean one of these, right? So AI is 0. That means one of the terms is basically missing. For example, this one, for example, right? The s squared is missing. Okay. So if you have a situation like that, one of them is 0, then the system is unstable. Because if there's a term missing, it basically guarantees that there's a positive root. The second thing you have to check first, again, as well, before you start doing this table I'm going to talk about, is if any coefficient AI again is negative, then the system is also unstable. Okay, so an example would be 2s3 minus 2s squared plus s plus 10, for example, right? There's a negative one here. That means it's also unstable. So just by inspection, you can look at these two rules and immediately figure out whether the system is unstable or not. Okay. So if there's a missing term, or if one of the coefficients is negative, then it's unstable. Now, if all the coefficients are negative, that doesn't count because I can multiply both sides by -1 and they all become positive, right? So that doesn't count. It has to be there's be a mix of plus and minus terms in the polynomial, then it's unstable. Now, if on the other hand you end up with a situation like sort of like this, right? Like that. So every term is present, and every term is and every term is positive. Well, rule 1 or 2 don't apply. So what do we do then? All right. So this is where the table comes in. Okay. This is where the table comes in. Okay. So we have to construct what's called a Ruth table. Okay. All right. So first of all, I'm going to construct it first for a second order, or basically a quadratic equation. So if I have something like s squared plus 3s plus 1 equals 0, okay? All terms are present and there's no negative terms. All right, so what do I do? So I'm going to label these A0, A1, A2, okay? Now, different books do this differently. Some books go from A0 to A2, which I like. Some books will go from A2 to go backwards, okay? So the last one becomes 0. I don't do that. But quite a few books do it this way, all right? So the table goes as follows. So the table you have to construct is, looks like that. You do 2 lines like that. And you go row by row, right? So the first row will contain A0 and A2. The second row will contain A1 and then a 0. The third row will contain this entry, A1, A2, minus A0, A3 divided by A1, and that's it. That's the table for the quadratic. Okay, second order. So why don't we compute this then, this table for this example, okay? So A0 is 1, A2 is 1, A1 is 3, stick a 0 there. I mean, you don't have to put the 0 there, but now you have to compute this thing. So I have to compute A1 times A2 minus A0 times A3 divided by A1, and I can tell you that happens to be 1 as well. That's the table complete. Now what you have to look for, you have to look in the first column and count how many sign changes there are. As you can see, there are no sign changes. They're all positive. The number of sign changes the number of sign changes, oops, right, equals the number of positive poles, positive rail parts, anyway, positive rail parts. Oops, because they could be complex, positive rail parts. So if this were -3, for example, I immediately know here's one sign change, 1 to 3, and here's another sign change, 3 to 1. I know immediately there are two positive poles. All right. Now, and in that case, I know then the system is unstable. However, in this case, of course, there were no sign changes. This system is stable. Okay. Excuse me. So that's basically how it works for a quadratic. Now, for higher order ones, it works the same way, except the table ends up with more rows and columns. Okay. So what about for a cubic? Okay, for a cubic. By the way, you might be wondering where this came from. This actually resembles the determinant. In fact, these are determinants of the minors within the matrix, because there's only one minor here, which is the whole thing. But basically, subsequent rows and columns are basically of this form here. Okay. Anyway, let's do the cubic. So for a cubic. So let's say I'll write down the cubic here, S3 plus A1 S2, oops, 2 plus A2 S plus A3, okay? So that's a cubic. So the table, I construct a table again. So we started with A, it's basically the same as this one, it just gets bigger, A2, A4. Basically the coefficients in the first row go up in evens. So if I had higher powers, I'd have an A6 here and so on, an A8 and so on. But I don't have that in this case. The next one starts with the odd numbered ones, A1, A3, right? But there's no A5, okay? So it stops there. In fact, there's no A4 either, so that wouldn't end up there either. But that's what it would do if you had an A4. The second one, the third rows are usually called Bs, B1, B2, B3, and the fourth rows are usually called C1, C2, C3, and so on. B1 in this case is exactly what it was before, A1, A2 minus A0, A3 divided by A1, okay. C1 is B1, A3, there's actually an A5 here, but we don't have an A5, so I'm not going to put that in, right? And then B1, okay, right? In fact, that just, of course, B1 cancels, of course. Now, so why don't let's do an example. Do I have an example? Yeah, I do have an example. Let's do an example, shall we? So let's do a very simple one. S3 plus S2 plus S plus 2 equals 0. Is this system, if this came from a transfer function, is this system stable or not? So we construct our table. So the first element has to be A0. This is A0, remember? A1, A2, A3. Okay, so that's 1. A2 is 1. A1 is also 1. A3, this one here, is 2. Okay. Now I have to construct this piece. That turns out to be -1. What's going on here? And then this one, of course, because the b's cancel, they don't cancel. You know, if you've got if you're bigger than a cubic, right? But they do cancel in this case. There was a term over here that disappeared. Okay. If I compute this one, it's A3, and of course A3 is 2. There you go. Now I look at the first column, and look, there's one sign change and one sign change. So that means there's 2 poles with positive rail parts. Okay. So it's unstable. All right, it's unstable. And if you could work out the actual roots for this. and that'll confirm that this is indeed the case. Now, what's interesting, you'll see this a lot. They come in pairs like this. They come in pairs like this because they reflect the fact that the two positive poles are actually a conjugate pair, right? So there'll be A plus BJ and A minus BJ, right? They're a conjugate pair, and you'll pretty much always find them in pairs like that, right? So it's on. You won't often find something like 1, 1 minus 1 minus 2, right? Because there's only one transition there. You'll often see 1, 1 minus 1, then back to positive. So that gives you the conjugate pair, right? Okay. And as I said, you always end up with conjugate pairs because the way, well, it's not, the system is nonlinear. It admits multiple solutions. And if you remember, you know, as I said, the e squared minus 4ac, the solution for a quadratic was that, okay? That's where the conjugate comes from, all right? Okay. What else? Okay, you might be asking, oh, this is all very nice. We have this table method that we can use, but do I really need it today in 2022? Not if this is all you were doing, the answer would be no. The real power of this now comes from the fact that these don't have to be numbers, they could be symbols, all right? So consider this example. S squared plus ks plus 4k minus 1 equals 0. So now I've got a constant in here. It's not actually a number, all right? And so the question I can ask is, example 4, what values of k is this system, stable? So this is the first hint, actually, of using this, of using what we've done so far up to now, week 7 or whatever week it is, the potential to do design. So I want a system that's stable. I've discovered this is the transfer function in my system. There's a tuning parameter I have here called k. What value should it be? Or should it be bigger than some value to ensure that this system is stable? All right. Okay, well, we can do that with this table. Right? I can construct a Ruth table. So let's do that. So the first one is 1. Now remember the Ruth table, it was A2, okay? And A2 is is 4k, okay? The next one was A1, which is k, okay? Then there's a 0 there. And the next one is this one, which was this thing here, A1 times A2 minus that. But remember, I don't have an A3, so that basically disappears. That cancels, and I end up with A2, which is 4k minus 1, okay? So I need to look at the first column. So I need to look for what would cause a sign change, or what really would prevent a sign change. Well, I need to go from positive to positive here. So this should be positive, right? I want to, let's say, have all positive entries. So in order to prevent a sign change, I need to have this positive as well. So 4k minus 1 should be greater than 0. In other words, 4k should be greater than 1. Therefore, k should be greater than a quarter. So long as this tuning parameter k is greater than a quarter, this system is stable. If it's less than a quarter, it's the potential for it to be unstable. Okay. Okay then. I think that will do for now. All right, and I'll upload this tonight. There's one thing I want to check before we disappear. Hold on for a second. Maybe I'll say something about the root locus method. Yeah, okay. Yeah, let me say something about the root locus method. I'm not going to say much about this. Just to let you know, all it is, for example, it basically plots the pole zero. There's a pole zero plot, and then it plots the, you know, the poles. And then what you do is you then might have some parameter, right, in your transfer function, and you want to know how the poles move as this parameter changes. And so that's basically what it does. So now you can see, so you might see something, you know, might see this moving up like this, or this one moving this way, or moving up or something. This gives you an idea of how the poles, sorry, are moving about in response to some tuning parameter in your transfer function. So you can get some idea of how the stability is being influenced by some parameter in the system. So that's all I was going to say about that. I think we're done for now. So I'm going to stop, and I'll see you tomorrow.